Problem set number 11, double integrals part 2. We're going to talk about mass in this video. Eventually we'll talk about center of mass and moment of inertia, but it's best if we introduce mass in this video. And little by little we'll work our way through all the various applications of multiple integration, which are good. It will give you a good motivation for this topic. Well, first of all, suppose we have this rectangular area we can define by a grid. Suppose we have a density defined as rho of xy kilogram per square meter. It's an area density, and we're talking about a two-dimensional figure. It can be a thin plate, but the density is a two-dimensional density. It's not defined along the third z dimension. So this would be x, this would be y, of course. If you take this little element of area over here, dA, dimensions dx and dy, dA is dy dx, and dm, a small little piece of mass, is defined as rho dy dx. You can check this out dimensionally. Kilogram per square meter times square meter gives you kilogram. You can just cancel out the square meters, and so dimensionally it works out. You get an element of mass, which is a kilogram. The mass integral we'll set up is rho of xy dy dx, integrating from a to b and c to d to integrate over this whole region. So we're starting fairly simple, but it's okay. Here's an example. Find the mass of a thin plate with boundary defined by 0,3 cross 0,8 or 0,5. That's this rectangle. And we have a density of x plus y kilograms per square meter. Just for example, down here we have density equals 0. Up here we have density equals 8. It's a linear function. Over here we'd have density equals 3. Over here we'd have density is 5, and of course it varies linearly in between. So if this were uniform density, if we had uniform density 8, it would just be density times area. 3 times 5 is 15, times 8 is 120. But 120 would overstate it, of course, because that's the maximum density. Halfway between here and here is 4. You could try 4 times 15 and get 60. And let's see how that compares to the actual density. So, or actual mass, sorry about that. So mass, you can just say m. Integral from 0 to 3, integral from 0 to 5, and we have x plus y dy dx. And we need to integral 0 to 3. We need to integrate with respect to y, gives you xy plus y squared over 2. And that's from 0 to 5 dx. And let's see, plug that in for y, it gives you integral 0 to 3 5x. Y squared over 2 is 25 halves. I'll call that 12.5 dx. And this gives you 5x squared over 2, or 2.5x squared, plus 12.5x. You can always do this with fractions if you want. 0 to 3. And plug in 3 gives you 9 times 2.5 plus 12.5 times 3. And let's see, that's 22.5 plus, and that's 37.5, and 22.5 and 37.5 adds up to be 60 kilograms. And let's see, that's halfway between here and here. That's 4 times 15 is 60. Surprise, surprise. Want to do another example, which is good. Good illustration. Number 2, let's suppose we have rho of xy is equal to 2y kilograms per square meter. And we have this region defined by 0,2 cross 0,3. You can draw a rough picture here, 0,2, 0,3, x, y. It turns out the density only varies with y. And so right here, for instance, the density is 2 times y, it's 2. Right here, the density is 4. And right here, the density is 6. 3 times 2 is 6. This is 2 and this is 3. So you can, as you move relative to the x-axis, the density is constant. So we can set up our mass formula and integrate from 0 to 2, 0 to 3, and density is 2y dy dx. This is our trusty double integral formula. It always works, 0 to 2. And 2y gives us y squared from 0 to 3 dx. And that gives us y squared, gives us integral 0 to 2, 9 dx, 9x 0 to 2, and we get 18 kilograms. Okay, and not surprising, actually, between 0 and 3, the average density is going to be right here. At 1.5, 2 times 1.5 is 3. The average density is 3. 2 times 3 is 6. 3 times 6 is 18. That's a linear function. But now what I want to do is show you how you can do this as a single integral. The density varies with one variable, y. We can integrate along the y-axis and do a single integral. When do we need a double integral? If the density varies with two variables. We did x plus y. X plus y, you have no choice but to integrate along both axes as a double integral. If the density would vary with depth, if you had a three-dimensional density, then of course we would have to use a triple integral. So we can simplify this. Let me draw you a slightly a new picture here. Let's suppose we have same thing, this rectangle, and that's 2, that's 3, y, x. And let's take a little rectangular element here. And we're going to break this thing up into slices. Well, this rectangular element, you can draw off to the side here. And we'll clear some space here for our integration workspace. This dimension here is 2. This dimension here is dy. And so we can say dA is 2 dy, just length times width, simple as that. And the mass is just simply density times area. As you can say is rho dA. And in this case, rho is equal to 2y. And that's times 2 dy. That is what we are going to integrate. And so the mass is a single integral 2y to dy, and y has to go from 0 up to 3. So 2 times 2 is 4, 4y squared over 2, 0 to 3. Okay, and that's 2y squared. We get 2 times 3 squared, which is 18 kilograms. Surprise, surprise, same answer. Okay. If this density were solely a function of x, well, guess what? We could integrate along the x-axis to get the answer, but not y. So, okay, that's all for this video. We'll be back to talk about volume shortly.